My name is Martin. I'm one of the guys that helps run the events of the Bulgarian Java user group. I do quite some research and some conference talking about Java security, latest security enhancements, Java secure socket extensions, and things like this. I just recently also wrote a book on RabbitMQ, so if any of you is interested in enterprise messaging, we can discuss any topics related to RabbitMQ after the session. But in particular, so most of you know that the field of Java security is a fairly tough and complex topic. It has a lot of aspects. And just before we start, and I'll show you what is the talk about, how many of you know what a security manager is in the JDK? Has someone had to use or to enforce some kind of permission checking in your code? Not really? Okay, so JDK security is very involved in a lot of projects. And since when we start talking about security, we start thinking of different aspects such as authentication, authorization, the JDK, bytecode verification, and different kinds of aspects. I've tried to summarize all of these topics in a tool called Java Security Animated, which I'll show you today. The idea behind the tool is that it's a visual tutorial that guides you throughout the different areas of security in the JDK and allows you to exercise some of the concepts which the JDK has put over the years in the platform. So the tool, it's basically a swing tool, which is divided into different sections, and we'll follow the logical flow. So we are going to talk about the core Java runtime environment and what are the security concepts put inside the JRE environment. And then we'll see what are some additional JDK utilities which are provided by the JDK that you can use to further secure your Java applications. So let's start talking about the Java runtime environment. So, as you know, before you start doing something, you write the code, compile it, package it, and deploy it. And this is where all the fun begins. So in the first place, before any classes are loaded by the Java runtime environment, there is the so-called bytecode verifier. And the purpose of the bytecode verifier is to make sure that the structure of your Java application follows the Java language specification. And the bytecode verifier does a number of things based on the data and control flow graph of your Java application. And to give you some insights, these are the number of things that the bytecode verifier does. For example, each Java class file is checked whether it follows the correct format according to the Java language specification. The bytecode verifier checks that all the code follows the particular access restrictions that you have implied. It checks things like local variables are used in the proper scope, and that final classes are not subclassed or final methods are not overridden. It also checks that every single class has a single superclass. There are no illegal data conversions, and there are no operand stack overflows and underflows, meaning that you don't pass more parameters to a method execution or you pass less parameters. Most of these checks can be done just before your classes are loaded. So the bytecode verifier plays a central role to make sure that your application follows the Java language specification. And this is really the first thing that happens just before class loading kicks in. So after bytecode verification is done, second phase is class loading. And as you know, basically the class loader is the central mechanism in the JDK that allows you to load your Java classes into the Java runtime environment so you can use them. One specific thing is that since JDK 1.2, the so-called secure class loader is introduced in the JDK. And the secure class loader really enforces the core JDK security platform model in two different aspects. So, as you know, different environments like Java EE and OSGi, they make use of different kinds of class loaders to load Java applications. And those class loaders are implemented using different kinds of algorithms that do different kinds of checks and so on and so forth. And the secure class loader is introduced in JDK 1.2, and as we already said, it outlines the security model of the JDK. So the secure class loader is pretty much implemented by the different kinds of custom class loaders that are out there. And the purpose of the secure class loader is twofold. The first purpose of the secure class loader is to assign every class of your application the so-called protection domain, which contains the location of where your class has been loaded from, the set of permissions that apply to that class, and that set of permissions is specified in the so-called security policy file, which resides in the JDK installation. And the other purpose of the secure class loader is to enforce additional permission checks. For example, whether your application can create an instance of a class loader and whether it can be used to load some third-party plugins or other applications. So these are the two main purposes of the secure class loader, which outline the security sandbox model of the JDK. I'm playing forward because the application basically is playing back and forth. So by default, there is a several seconds interval where all the slides play, but I'm stopping them so I can describe you the concepts. So an additional point to make is that the protection domain, as we said, contains the location of where a particular class is loaded from. For example, a jar file, some location over the internet, the file system, and so on and so forth. However, there is also something else which fulfills the protection domain, and that's the set of JAAS principles. How many of you know what JAAS is? I see just one person. So JAAS is the Java Authentication and Authorization Service, which is the de facto standard mechanism in the JDK to provide authentication and authorization capabilities in your application. And the JAAS API basically fulfills the security sandbox model of the JDK with the possibility to do permission checking based on the permissions of the currently logged in user. So JAAS has two parts. It's the authentication part that allows you to provide different kinds of authentication mechanisms for your user, such as, for example, you have a GUI window, or you authenticate your users using a database or an LDAP server, and so on and so forth. And it has also an authorization part, which allows you to specify particular permissions in the security policy file that are bound to that particular user. And let's say that, for example, you can specify in your security policy file that all the users that have a particular, let's say, email address or some LDAP attribute and so on and so forth have the possibility to, let's say, open a socket connection or delete a file on the file system. And however, since JAAS principles, which are the attributes of the user, are also part of the protection domain, they are not set during class loading. And the reason for that is basically because the user is authenticated already when the classes of your application have been loaded in the Java runtime environment. And for that reason, the JAAS API extends the permission checking model of the JDK with the so-called dynamic permission checks. Okay, so moving forward, we saw briefly how does bytecode verification happen, then how does secure class loading happen when you load classes in your JDK platform. And now let's talk about automatic memory management. As you know, all of us know that Java provides automatic memory management in terms of the Java heap space. And we have different kinds of areas of memory which are managed by the JDK. We have the heap. We also have the thread stacks, which are the areas that keep the local variables created by each of the threads that you create in your application. We also have the constant pool, which keeps track of all the constants that you're using in your Java application. And we also have the method area, which keeps all the definitions of the methods in your Java classes. So these are typically the areas of memory that the JDK keeps track of. And typically, because of this automatic memory management mechanism, the JDK is very secure in terms of that you cannot execute certain types of attacks, such as, for example, buffer overflow attacks, which are very typical to the C++ programming language. There you can basically exploit and inject some additional instructions in memory that's not being checked by your application. And in the JDK, that's not pretty much possible. However, in certain cases, for example, if you make JNI calls, or if you create and use off-heap memory, which is something that's quite used for performance optimizations. For example, different messaging applications and different caches use the off-memory heap, which basically is a memory that's not managed by the JDK. There is still some possibility of attacks related to buffer overflow. But that's really very narrow, and it's not very common to the JDK. Another aspect of security in the JDK is strong data typing. As you know, in the JDK, variable types must be specified explicitly. And in case basically some information cannot be deducted at compile time, and some verifications cannot be done by the bytecode verifier on the correctness of the types that you define and the casts that you do, some additional checks are done at runtime to make sure that all the type information in your Java application is correct. However, there is still some possibility to exploit the type system in Java. There is a certain set type of attacks which is called type confusion, whereby you can whereby you can achieve casts that are not typically allowed by the Java language specification. And that's pretty much the case if you use some of the APIs of the unsafe class, which is already deprecated as of JDK 9, but it still opens some doors and possibilities to trick the Java type system. These types of attacks are also not very common, and they're a bit difficult to achieve, but there is still some possibility to trick the Java type system into this kind of attacks. And now, moving forward, the really guts of the JDK platform is the sandbox model. So the sandbox model of the JDK is really provides the possibility to sandbox what particular areas of your code can do with the environment. So the main reason why the Java Security Sandbox was needed was because when at the time Java applets started appearing and the possibility to execute code from the client's browser was already very widespread, there was really a necessity to somehow say, okay, this particular applet is only allowed to write to this particular location on the file system. At the time when applets were introduced, the JDK didn't have any way to sandbox execution of code on the client's environment, which introduced a huge security concern. And that's why the security sandbox model was introduced. So it basically allows the execution of untrusted code, such as Java applets on a client environment, or any applications that are being deployed in another managed environment, like a Java EE application server or an OSGi runtime, to have just a certain set of permissions that are allowed. And over the years, basically, this model has been successfully applied in different areas, not only Java EE and OSGi, but also, for example, if you write, let's say, Java stored procedures in your Oracle database. So Oracle database runs just a minimalistic version of the JDK that provides a security sandbox model for the Java stored procedures, whereby additional permissions that are required by these Java stored procedures are checked against a relational database table. And here the security manager is quite customized. By default, the JDK, as we said, uses the security policy file, which is part of the JDK installation, and lists all the permissions to your classes. However, there are some customizations that are done, such as, for example, is the case with Oracle database, that still leverage this security mechanism in a different way. So the security sandbox model, there are two main APIs that allow you to do permission checking in the JDK. These are the security manager and access controller APIs. And the main difference between the two is that the security manager is an older API. The way it works is that you need to have an instance of a security manager installed in your system in order to do permission checking. By default, all the Java applications that you write, they don't have a security manager installed, and they can do whatever they like with the environment. Let's say they can write to a file system, they can open a socket connection to any website, and so on and so forth. However, most of the application servers out there, they use a security manager installed by default that restricts heavily what applications can do with the client's environment. And the access controller API is just a newer API, which does pretty much the same as the security manager API. It's used to do permission checking. However, the security controller does not need to be installed in your Java application. And it just provides a set of static methods that you can use to do permission checking. So the way you can set a security manager is, for example, by calling system.securityManager at the beginning of your Java application, or you can do that outside of your application by using the Java Security Manager property when you run the Java runtime environment. And yeah. And for example, if let's say we have some permissions defined in the security policy file, A sample entry of such a permission looks like this. We say grant code base, and then we specify the location of where our classes are loaded from. In that particular case, I have some location on the file system, and all the classes that are located in lib.jar have the permission to delete the cwindows folder. And in a similar manner, you can specify permissions for the different classes. As we said, this forms the protection domain of the classes in your Java application. For every class, you can say class.getProtectionDomain and receive information about the code base. In that particular case, for all the classes, that would be lib.jar, and also the set of permissions, which in our particular case is just one, that's file permissions. So let's say that we have that defined in the security policy file, and that jar, lib.jar, is part of our class path. When basically we do that, automatically we receive some properties which are specific for the Java security model. For example, the fact that we have specified that we can delete the cwindows folder implies that we can delete any subfolder under cwindows. For example, we can delete also cwindows system32. And also the fact that we have specified location for our lib.jar in C project's libs. This implies all the subfolders as well. So all the jars loaded from sublocations also have the file permission. This is a very useful property of the Java permissioning model that allows you to specify permissions in a more compact way, not having, for example, to list all the file permissions or all the code locations and all the subfolders. Okay? And as we said, so the protection domain for each class is set during class loading. And it encapsulates the information of where our classes are loaded from and the set of permissions. You can get it using the get protection domain, which is on the class instance. And then when the permissions are set during class loading, you can use the security manager to do permission checking. In many places inside the JDK code base, there is a certain set of checks which checks if you have a security manager installed, do some permission checking. For example, if you try to write to the file system, behind the scenes the JDK does a permission check which is in the form if a security manager is installed, then security manager.check permission, new file permission, something. And this is also the case in most of the Java EE application servers. For example, if a WAR file tries to, let's say, open a socket connection to a URL, the Java EE application server checks whether the particular class from your WAR file has the socket permission required. And the way it works is like this. So this is an example. For example, if you want to check whether your currently executing code has the socket permission, to open a socket connection to github.com on ports 8000 to 9000, you can create an instance of a socket permission. Each permission in the JDK has typically 2 or 3 components. So in the JDK, there are around 30 standard permission classes defined, such as socket permission, file permission, runtime permission, whether you can do reflective calls, and so on and so forth. You can define your own permissions if you like. And in that particular case, the socket permission has 2 parts. This is the location that we are checking, and also the type of connection we are doing, whether we try to connect or whether we receive connections from that location. And then we check whether we have a security manager instance installed. The way we do this is by calling system get security manager, and if the instance that we get is not null, we call the check permission method. The check permission method is really the core of the Java Security Sandbox model. What it does, it takes the current call stack of where that execution happens, and it checks that all the classes in that current call stack have the socket permission. Even if there is a single class that doesn't have the socket permission, there is a security exception thrown. And this is basically the way that permission checking works in the JDK. You can do pretty much the same with the access controller class. So if you don't want to install, or for some reason you cannot install a security manager, you can do the permission check using the access controller class by calling directly the static check permission method. And also there are some additional operations that provide you more flexibility when working with the Java Security Sandbox model. For example, you can change the currently logged in user. A user is represented by a JAAS subject instance. The subject class is provided by the JAAS framework that represents a currently logged in user in the system. Where you authenticate a user using JAAS in your JDK application, a subject instance is created. And using the subject.doAs method, you can basically switch the current user which runs the Java application, thus eventually providing another user which has a different set of permissions. And you can also do privilege escalation. Privilege escalation is achieved using the access controller doPrivileged method. And privilege escalation basically works in terms of it keeps basically the entire call stack up to the point where you call doPrivileged. A very good example of this is, let's say you have some Java EE application that wants to write something to a log file. However, the Java EE application server restricts all the applications that are loaded to write to the file system. However, the application still tries to use, let's say, a logging service from the Java EE application server. The Java EE application server has one particular protection domain, and the Java EE application has another protection domain. So the way to achieve that is by escalating the privileges of the current application in the logging service used by the application server. So the application server will do access controller.doPrivileged, and will in the doPrivileged block it will provide the capability to write to the file system. In that particular case, the current call stack skips all the classes from the Java EE application, which are typically restricted to write to the file system. And in that way, we provide the capability to write to the logging service. And also, if you want to specify some attributes of the currently logged in user, you can also do that in the security policy file. Let's say that you authenticate users against an LDAP server. In that particular case, you specify that if the user that's currently running your Java application has this LDAP attribute, which is some name equals Tom, then that user has the possibility to delete the cwindows folder. This is an example of dynamic permissions. So at the time of class loading, as we said, these are not set on the current class instance. However, when you log in some user in your Java application using JAAS, and that user basically has some particular set of principles, when this user needs to achieve something with the file system, let's say it tries to delete cwindows temp folder, then the security manager basically consults the security policy file and the permissions of the currently logged in user to do the permission checking dynamically. So there are certain set of enhancements. The security model, which remains up to date, is the one introduced by JDK 1.2. It hasn't been changed a lot over the versions of Java. There are some enhancements introduced, but really this is the core security model which has been built in the platform since more than 15 years now. And however, since some of the recent versions, there are some changes, smaller improvements and changes to the model. For example, there are some certain improvements introduced as of JDK 1.5 and 1.6, such as, for example, LDAP support for JAAS, which wasn't there before that. And there are some new methods provided on the access controller API, such as, for example, a method that allows you to specify just a subset of permissions to check against. That wasn't out there in earlier versions. Also, in JDK 9, when the new module system is introduced, how many of you have heard of Project Jigsaw? Okay, like 10 people. So the new module system in JDK 9, as most of you know, splits the huge and monolithic JDK into multiple modules. We have more than 5,000 classes in the JDK split into different kinds of modules. And the way that we need to work with modules is that the security sandbox model remains pretty much the same with modules. However, there is one additional attribute added, and that's the possibility to specify a runtime module in the security policy file. So you can specify particular permissions that apply on your Java module in the security policy file. There is a new protocol introduced, JRT, and using that protocol, you can specify the name of the JDK module for which the particular permissions apply. That's the major change here. And as you can see, the security model remains the same. All the classes from the JDK module are assigned the file permission, which is to delete the cwindows folder. And that's it. So that's pretty much the security sandbox model in the JDK. Now, this is what's been built in the platform in the Java runtime environment. However, on the other side of the coin, we have a number of security utilities which the JDK provides, which we can use directly in our Java applications. And these utilities are used, for example, to open secure socket connection, or to enable TLS, or to do some certificate revocation checks, to work with public and private keys, with certificates, and so on and so forth. So if we are to talk briefly about those kinds of utilities, let's first talk about JSSE. And why do I start with JSSE? JSSE is one of the APIs in the JDK security portfolio, which have been mostly updated and supported in latest versions of the JDK. So the JDK supports the TLS series of protocols through the Java Secure Socket extension. The Java Secure Socket extensions works pretty much in a similar manner as you would do with standard Java sockets. However, there are a few other things you need to keep in mind, such as how you can trigger the TLS handshake process when you establish communication between the client and the server. And the TLS handshake process can be triggered in several different ways when you create the client and server's TLS sockets. We'll see an example of this. So, as you know, the TLS set of protocols is the de facto standard set of protocols that allow you to secure communication between parties. It also lays the basis of creating the so-called SSL VPN types of VPNs that you can use. And there are two modes of operation of the Java Secure Socket extension. The blocking mode of operation is the one that pretty much is used by most implementations that make use of JSSE. And it's the one that makes use of Java client server sockets. And there is a much more complex way, asynchronous or non-blocking mode of operation, which is not that popular and not that used in the JDK because of the complex implementation and a number of corner cases you need to consider. And up until JDK 9, TLS 1.2 is supported by the JSSE API. Just recently in JDK 11, support for the TLS 1.3 series of protocols was introduced. And the TLS 1.3 series of protocols introduces a number of improvements over the TLS handshake process in terms of performance, in terms of improved security, in terms of new features which are provided by the protocol. Let's look into some more details. So before parties can in fact start exchanging messages with TLS, there needs to be a TLS handshake process established. And the TLS handshake implementation is not visible for the developers. So when we start using the JSSE API, we don't need to consider establishing explicitly the handshake process. Behind the scenes, the JDK triggers the full process, which is, let's say, the client tells to the server, okay, I support version 1.2 of TLS and this set of cryptographic chiffres. The server says, okay, let's use TLS 1.2 and this set of chiffres to start negotiating. Then the server sends its public certificate to the client, and the client takes the public certificate and verifies that it is not revoked by a certificate authority, that it's still valid. And optionally, the client may also send its own certificate to the server. At that point, they start using the certificates that they've exchanged to generate a secure key. And then that secure key is used to encrypt communication between the client and the server. This entire process is implemented behind the scenes by the JSSE API. And we have different ways to trigger the handshake. We can explicitly call the start handshake method on the socket, on the client or server socket. Or when we try to read or write to the socket, the handshake process is triggered if it's not triggered already. So this is an example of a simple Java Secure Socket extension server. Here, the first thing is that we need to specify the key store that stores information about the public certificate of the JSSE server. And then I also specify some password for the key store. Then I create an instance of an SSL server socket factory, which is used to create a server-side SSL sockets. Then I create one server SSL socket on port 4445. And then I accept some connections. At this point, this operation, as you might guess, is blocking. So this is the blocking mode of operation of JSSE. And then I read the input that's been provided by the client and print it out. And at the end, I send some information, some message to the client, hi client. And in a similar manner, this is how a TLS client looks like. In the TLS client, I specify the trust store, which stores the set of certificate authorities that the client application trusts and that it uses to verify the public certificate that's been sent by the TLS server. Then I create an instance of SSL socket factory, which is the client SSL socket factory, and I create a client SSL socket again on the same port, 4445. And then I send some information to the server and print it out. Here in the application, in fact, you can observe what's happening if you execute the TLS server, for example. And then you can also execute the TLS client. And they start exchanging communication with each other. So the idea is that in the application, you can run pretty much many of the examples here using the tool. And one thing that's currently in development, and I cannot show it to you, is that there will be some exercises that you can use to play around with some of the new features around the TLS protocol improvements in the JDK. Okay. So this was the Java Secure Socket Extension API. We already mentioned briefly JAAS, or the Java Authentication and Authorization Service. It's introduced all the way back since JDK 1.4. And it, as I already mentioned, it has two purposes: to provide authentication and authorization capabilities in the JDK. However, many application servers and Java frameworks really don't make use of JAAS. Although the original intent was that the JAAS framework would be very widespread, it would be used as a de facto standard for authentication and authorization in the JDK. However, that's not really the case. However, the JAAS framework is very pluggable. You can provide different authentication mechanisms and combine them. You can define different rules to, let's say, I want to authenticate a user against a relational database, and if that fails, fall back to an LDAP server and so forth, so on and so forth. So you can create pretty complex authentication flows using the JAAS framework. And there is a certain set of classes that are really specific to the JAAS framework. So a user that's being logged in your JDK application is represented by the JavaX Security Out subject class. Each user has one or more principals, which is the set of attributes to the user. For example, a user might have an email address, a username, and some other attributes. This is specific to the login module that really is used to log in the user. A login module is basically the component in JAAS that allows you to really authenticate a user against a particular third-party system, like a relational database, an LDAP server. In the JDK, there are several different implementations of login modules, such as one for authenticating against a relational database, against a file on the file system, against LDAP server, and several more. And really, the starting point for all the developers to use the JAAS framework is the login context class. A login context basically reads all the information about the currently defined login modules from a central JAAS configuration file that you need to create in your application. And based on that configuration file, you can start authenticating users in your Java application. And that's since JDK 1.4, you can use it out of the box with all versions of JDK that you install after JDK 1.4. Okay, that's briefly about JAAS. A few other APIs which are worth mentioning is the JCA, the Java Cryptography architecture. So the Java Cryptography architecture is pluggable. The JDK doesn't really have the responsibility to provide any implementations of cryptographic algorithms, for example, for creating digital signatures or message digest. However, the JDK does provide some default implementations. For example, there is the Sun JCA provider, which provides a number of implementations of the different APIs by the Java Cryptography API. One of the biggest and most widely used Java security libraries that implements the JCA is Bouncy Castle. How many of you are using the Bouncy Castle? A few people? Okay, so Bouncy Castle, I would say, is the biggest provider of JCA algorithms. and it's very well supported. So in terms of bouncy castle and the default provider implemented by the JDK, there is a fairly good amount of different utilities you can use, and you can also create your own if you need to. Another utility in the JDK is the GSS API. So the GSS API is an alternative to the Java Security Socket Extension API in a way that it allows you to secure communication between a client and a server. However, to do that, it uses so-called security tokens to exchange secure information between a client and a server. So you can use the GSS API instead of Java Security Socket Extensions. And GSS API is typically used with the JAAS framework to provide authentication using the Kerberos protocol. The Kerberos protocol can be used to authenticate users against a Windows server or a currently running Windows operating system. And the way the Kerberos protocol works is by exchanging secure tokens, which is basically an implementation of the GSS API. And the JDK provides out-of-the-box implementation for the Kerberos series of protocols. Another API which you can use is the SASL API. A SASL basically defines protocol for exchange of secure communication between a client and a server. It allows you to negotiate what kind of authentication channel would a client and a server use. The way it works, for example, is a client sends to the server information that it can authenticate using an email address or, let's say, some database attribute. And the server tells the client, okay, let's communicate by providing me an email address. And so the client starts authenticating using the server by providing an email address and optionally some additional information. So the SASL framework, in fact, provides you with capabilities to negotiate what should be the secure information that needs to be exchanged between the client and the server. There is a certain set of utilities that allow you to deal with public key certificates. And the way it works basically is that there is a class in the JDK that represents a public certificate, and as you know, you can store those certificates in the so-called key store. By default, before JDK 10, the default format for storing public certificates was JKS or Java Key Store. And however, they switched that to the standard PKCS 12, which is a more well-developed specification, not really specific to the Java platform, but specification on how you define a particular key store for storing public certificates. So that's something that's changed since JDK 10. The JDK also provides you with utilities to check whether the certificate is valid against the certificate authority. And that can be done in two different ways, basically either using revocation lists, which is basically a flat file of certificates that are already revoked by the certificate authority, and that's published on a regular basis by a certificate authority, or using the OSSP protocol, which basically is a more complex protocol that allows you to verify against the certificate authority that a particular public certificate is not legitimate. And that's what pretty much the PKI utilities provide. We also have some utilities that allow you to sign jar files or XML files. So jar verification was out there since when Java applets were introduced. When applets were introduced way back in JDK 1.2, we needed a way basically to sign applets in order to specify that these applets are trusted and they can do whatever they like with the system. So they were given all full set of permissions. So in order to sign a jar file or an applet file, you can use the jar signer utility, which is part of the JDK installation. You specify the jar file and the public certificate to be used. That public certificate is retrieved by default from the key store that's specified that's out there in the JDK, but you can also specify a different key store location and password. And yeah, that's the jar signer utility. You can also verify that a signed jar file hasn't been changed using the jar signer utility again with the -verify option. And you can also specify the certificate, the key store to use, and so on. And there is something similar as an API in the JDK which allows you to sign XML files. And that's basically the implementation of the XML Signatures API, which is a web standard that allows you to encode information about a particular XML file in the XML file itself. That's the format of this signature that you can put pretty much on any level of your XML file. Could it be the full XML file or just a particular block in the XML? You can just sign a particular block. And the JDK provides an implementation of the XML signatures API, which works in a pretty much similar way as jar verification. So in order basically to use the XML signatures API, you need to follow the following process. So you need to get an instance of the XML signature factory class, and that is used to create a reference to the document or block of the document that you want to sign. Then you create an instance of your public certificate that you're going to use for the signing and wrap it in a key info object. And then you use the created XML signature factory and key info object to sign the XML file. That's pretty much the process you can use. The XML signatures API is in the JDK since 1.6. And those are pretty much the major APIs which you can use and are building the JDK. Now, what I've showed you basically is currently being developed in several different directions in addition. So there will be more exercises here you can play around with, and you can basically use the tool to exercise some of the concepts. We basically haven't covered all the full set of enhancements introduced in latest JDK versions, such as some of the TLS enhancements. So latest versions of the JDK, such as 9, 10, 11, introduce a lot of improvements on the JSSE API, or the support for the TLS in the JDK. They introduced things like ALPN, which is Application Layer Protocol Negotiation. That's basically the possibility to negotiate the application protocol during the TLS handshake process, which is very useful, for example, with the new version of the HTTP protocol. Let's say you have a web server that runs both HTTP 1.1 and HTTP 2.0, and you need to establish TLS between this server and different clients that support different versions of the HTTP protocol. And you can do that during the TLS handshake process. So there are a number of enhancements, and also the tool basically would provide more information about utilities in Bouncy Castle, additional security of frameworks like Java EE, OSGi, and Spring, which is currently work in progress. The current implementation is open source. If you want to see how the tool is implemented, you can go to GitHub or just search for Java Security Animated. This is the tool, and also as I already mentioned you, the tool is implemented in Java Swing. For the execution, I use the JShell API introduced in JDK 9. JShell, as you know, is a standard REPL for the Java platform. It allows you to play around with some utilities from the command line. And the JShell API also provides you with a number of utilities that you can use to execute a particular block of code at runtime. So I'm making use of JShell to provide the capability to run the snippets here from the tool. There are some alternatives to that, of course, some third-party libraries that provide you those capabilities, but JShell is in fact standard API of the JDK and much better choice for use. And I think that's pretty much what I wanted to show you now. Any questions about the tool or Java security? Yep. Yeah. Mm-hmm. Yeah. Well, if well, basically, when you do bytecode verification on a set of class files, you basically check in a set of classes. So bytecode verifier works across not one but multiple classes and walks through the instructions basically to make sure that you don't have a method that basically tries to be overridden. You can. I mean, if you use some tool, basically like, let's say some bytecode editor, there are tools like this. You can just go and edit it directly. I mean, and the bytecode verifier does it, because even though you compile the classes, you can edit them using some bytecode verifier. And it's still the purpose of the bytecode verifier to make sure that, although the compiler is not allowing this, you might change the structure just before you load it into the Java runtime. And that's why it does this kind of checks. Typically, in the majority of cases, that's not the case. I mean, you're not going probably to edit your class file. It's typically hard, but it's possible. And the bytecode verification checks it. Okay, other questions? If no, then thank you for attention. You can check the tool, you can provide some suggestions for improvements, contribute, anything basically. The idea is that this tool serves as a central place to lower the entry barrier of Java developers to the different aspects of the JDK security portfolio. I'm really actively working on that, and yeah, any ideas or contributions are more than welcome. Thank you.